Hello everyone, I hope you are doing well. So in today's video, I'll be going through the 2019 chemistry exam for the Northern Hemisphere multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Which of the following isomers of this has a chiral carbon? So first, what is a chiral carbon? A chiral carbon has a carbon that has totally different four side groups. For example, this could be like a OH, this could be a Cl, this could be a CH, this, or this could be a bromine. Can you see how all of them have totally different side groups? So this one has chlorine, this one has bromine, this one has an OH group, whereas this one has a methyl group. If they have totally 4 different sides, it is called pretty much this carbon is a chiral carbon. And so let's check which of the following has a chiral carbon. So let's look at the first one. So it's in its skeletal formula. So I'm going to write it as a normal. So C, 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 OH. And okay, I'm going to draw all of these hydrogens. By the way, these are hydrogens. I just draw them as straight lines. I mean, this one, this carbon is not a what we call a chiral carbon because it has both H's. Remember, it has to have different side groups, not the same. So these have H's. Also, this one has a H, both sides, H, and both H's. So this one has no chiral carbon. Let's look at the next one. All right. Let's also draw the next one. So it's a C, 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 OH, and a H here, and H here, H here. These are all side groups. What about this one? Well, this carbon absolutely doesn't have because it has HH. HH also for this carbon. But look at this carbon. It has a H group, that's one. Okay. OH, that's a different side group. A methyl group and an ethyl group. Beautiful. This carbon right over here actually does meet our requirement of chirality. So in other words, it must be B. Normally, look, I'll be honest, I just wanted to show you how to do it, by hand. But like, for example, if you're in an exam, you have to do it quick. For example, it's easy to look. If you just look at this, there's there's carbons in here, carbons in here, carbons in here. Well, there's no carbons that are chiral in this case. This one, okay, it has a methyl, ethyl, OH group, and a H here, an imaginary H. So it has to be that carbon. Let's try the next ones. For example, what about this one? This is a problem because we have, what do we have? We have a methyl, 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 and this carbon, and that's the only carbon. So what's happened? It's not going to be chiral because it has all those same groups. What about this one? This carbon has both methyl, that doesn't work, and this carbon has imaginary H's here. So both does not work. And that's how you can easily do this question. Nice and easy. Quite comes up in many exams, so it's quite an easy mark to get. Question 2. A galvanic cell is set up as shown in the diagram above. Bubbling is observed at one of the electrodes. From this evidence, it can be stated that, okay, the bubbles observed must be hydrogen gas. Well, how do we know that there could be chlorine gas or oxygen gas? That's not that we can't take this from like that. How do we have evidence for that? We're not giving any information. Electrons must be flowing across the solid bridge. No, ions flow through the solid bridge. Be careful. Electrons flow through the this circuit here, through the wiring here. So be careful of that. The two electrodes cannot be made of the same material. How do we know? Like, we don't even know what the electrodes are made of. Like, that's rubbish. We just can't predict nothing. What about D? There's not enough information to form a valid conclusion. That is your possible answer. They haven't given us anything to deal with. So yeah, will likely be D. Beautiful. Question 3. The correct IUPAC name for this molecule is shown is what? So let's have a look at this. So we have a chlorine and a amine group. Okay, what's first the longest chain, carbon chain? Well, it's this chain right over here, as you can see. Which is what? Do we start counting from here? 1, 2, 3. Or do we start counting from here? 2, 3. Well, you should be starting counting from here. 1, 2. Why? Because we hit the amine group first. If you start counting here, 1, 2, 3, we hit the chlorine, but it's on the third carbon. And remember, we want to hit the shortest. So it will be this right over here. So it'll be this part over here. This will be your 1. This is a 2. So at 2, we hit the amine group. 3, 4, and 5. Now, when we're writing, what is the highest, like, what do we normally, priority? Like, what's the highest priority functional group? You should know that amine groups have a higher priority than chlorine. So when we're writing the, for example, this is a pentane because it has 5. So it'll be pentane, and it occurs the amine groups at 2, so 2 amine. Can you see how we write the amine group? Because that is the highest priority. That's going to be the overall at the end of it. And yeah, so which one has that? Not pen. So this one's, okay, this is butane, no. It can only be A. And let's check if that's true. Yes, at 3, it does have a chloro. So beautiful. That is your possible answer for 3A. Beautiful and nice. A catalyst for a reaction will reduce the difference between the energy of the product and the energy of the reactants. The way we can represent this is, okay, let's draw a, what we call energy profile diagram. So let's say this is a, I don't know, exothermic reaction. So this is the energy. Right over here is the energy of the reactants, and this is the energy of the products. If we're reducing this energy barrier, are we reducing? We're reducing the change in H, the change in enthalpy. And what do we know? That change in enthalpy is not affected through a catalyst. It doesn't actually get affected. The only thing that affects a catalyst affects is the activation energy. So that's rubbish. Increase the proportion. Let's look at the next one. So let me rub that out. Increase the proportion of successful collisions at a given temperature. Well, the way we actually can represent this is by a Max-Boltzmann graph. For example, if I draw a Max-Boltzmann graph, just to represent this, we know a Max-Boltzmann graph will look like something like this, and nicely like that. Okay, so let's say the activation energy is here. That's your activation energy. What do we know? So at this point, remember the area represents the number of molecules. So over here, these molecules don't have a sufficient energy to overcome the activation energy. So whereas these over here, these molecules actually have sufficient energy because they overcome this activation energy, and pretty much, yeah. So a catalyst for a reaction will, no, remember what we talked about? A catalyst decreases the activation energy. So if we put a catalyst, the activation energy becomes now here. And guess what happens? Now look at the area. It's much greater. So now there is more successful collisions. As you know, more molecules are able to go above and beyond the activation energy barrier. So a catalyst for a reaction will increase the proportion of successful collisions at a given temperature. Beautiful. That is the best definition you can give here. Because you remember the area here. So there's much more... we've just pretty much increased the success. There's more, atoms that are more successful in collisions. What about C? Requires an increase in temperature in order to work. No, you don't. That's rubbish. Only works for gaseous reaction, can work for others. So that's not right. Beautiful. Question 5. The table below gives the heat content in kilojoules per gram of a number of different fuels. So what do we have? We have the heat content, biogas, biodiesel, black coal, bioethanol, and petroleum gas. Given the information above, it can be stated that petroleum gas is pure methane. Well, if it was pure methane, what do we know? It should have the same energy content as methane gas in terms of kilojoules per gram, if it was all pure methane. And we can check that. So look at petroleum gas, it's 54. So if I go to my data booklet, so go to my data booklet, what do we can see? Well, go down, here we go. Methane, the gas, actually, as you can see, here's methane. In terms of kilojoules per gram, it's actually 55.6, but here it's 54. So if it was pure methane, it would have been 55.6. So there must be impurities. It's not actually pure methane. That's that. So we can straight away, that's not a true fact. Easy. So that's wrong. B, all of the fossil fuels produce more energy by mass than renewable energy sources. Remember, the renewable energy sources are pretty much those that have bio in. For example, here, this one has bio, and bio. These are renewable energy sources, whereas the others, like black coal and petroleum gas, are non-renewable or fossil fuels. So it says all of the fossil fuels produce more energy by mass. Well, let's check that. Absolutely rubbish. As you can see, biodiesel, which is a biofuel or renewable energy source, guess what it has? It has a higher energy content than black coal. So That's not true. Perfect. C. The renewable energy source that produces the most energy by mass is biodiesel. Remember, the renewable, so biofuels, that produce the most energy. As we can see, let's look at the bio. Well, the only one that has the highest from these three is biodiesel. So that's actually right. So we can put a tick down there. Biogas can be produced from renewable energy sources. That's true. And produces more energy by mass than petroleum gas. Well, so what is it? Biogas. Where's biogas? No, that's wrong. Petroleum gas produces more energy than biogas, as we can see. So that's rubbish. So your possible answer is C. Question 6. A sample of food contains 12 grams of carbohydrates, 7 grams of protein, and 5 grams of fats. The energy content of the sample is... What a beautiful question. It's very nice and easy. So the way you do this question is just go to our data booklet. And okay. So first let's look at that 12 grams of carbs. So right, 12 times. How much energy does a gram of carb give? So it gives 16. So we want to multiply by that. Plus, we have 7 grams of protein. And how much does protein give? It gives 17. Plus, how many grams of fats? We have 5 grams of fat, which is 37. And remember, all this will be in terms of kilojoules. So let me just... All right, perfect. So I'm going to do that on my calculator. So 12 times 16 plus 7 times 17 plus 5 times 37. Beautiful. That will give us 496 kilojoules. Beautiful. Which is A. 6 is A. Question 7. Which of the following statement indicates why ethanol produced from sugarcane is defined as a biofuel and ethanol produced from coal is not? Okay? Now, you should straight away know it because what is a biofuel? Well, it can be renewed quicker. So, this is the definition. Sugarcane can be grown quicker. As we can see, it can be replenished as quick as we are consuming it. Whereas, coal is a problem because it takes millions of years to produce. So, it's not very renewable. That's why the definition is. So, let's see if those answers meet those conditions. Ethanol produced from sugarcane generates less greenhouse gases when used as a fuel than ethanol produced. Well, that is true, but does that answer why it's a biofuel? No, it doesn't. Remember, so B. Ethanol produced from coal can be used to generate electricity, whereas ethanol produced from sugarcane cannot. Rubbish. Both can be used to produce energy. Produce electrical energy. Don't think of it as, because it's made out of, plants and animal matter, that it can be used. It actually can. So, rubbish. Sugarcane is recently living organic matter, whereas coal is formed over millions of years. Beautiful. That is the perfect definition. Coal is formed over millions of years. That's why it cannot be, replenished as easily. And that's why it's not a biofuel. It is a fossil fuel. Whereas sugarcane is easily, it's a recently living. So you can easily grow it. And so, see, we can put a tick on that. Let's look at the next one. Sugarcane is a natural resource, whereas coal is not. Rubbish. Coal is a natural resource. It is formed from the decomposition of plants and animal matter over millions of years. So, the only possible answer is C. Use the following information to answer A and 9. Okay. A student designing an experiment to determine the concentration of aspartame in soft drinks uses high-performance liquid chromatography. Aspartame, benzoic acid, and caffeine are all common components of soft drinks. Under some conditions, they have similar retention times in HPLC column. Okay. The graph below shows the retention times for these substances at different pH values. Okay, so we can see retention time on the y-axis and pH on the x-axis, and we can see that we've given a key. According to the graph, which pH value will provide the largest separation of aspartame, benzoic acid, and caffeine? Well, let's really think about it. Let's look at the first answer, 3. So pH of 3. Let's look at 3 here. So if I was, think of HPLC. So we have a chromatographic paper here, like a nice paper. And we're going to put 3 samples, like that. All right. So this is for pH of 3. What do we know? Well, the retention time of, in this case, is benzoic acid is what? It's 7.5. So it's actually the longest. And what does that mean? So if the retention time is very long, the actual For example, benzoic acid, when it's, dripping down, it's taking very long to go down to the ground level here. So if it takes that long, what do we know? Let's say it would, take very long. So it would likely to be over here if it's taking that long. It would likely to be like somewhere around, I'm going to write B, benzoic. So let's say let's say 3 seconds. Let's say everything's measured in 3 seconds. Benzoic acid in 3 seconds will be over here. It wouldn't move a lot. It wouldn't have moved a lot because the retention time is very, very long. It takes quite a long time to actually reach the bottom. Whereas, let's look at aspartame. We can see that it's much shorter. So it will probably be over here. Likely over here because it's much further. So, yeah, it would take... so in that 3 second, let's say in that 3 second mark, where just, it will take less, it go quicker than benzoic acid, so that's aspartame. Then the last one, which is caffeine, which goes quick. The retention, so it will, in let's say 3 seconds, caffeine, it will go straight away down. So what do we see? Well, the question is telling us, which pH value would provide the largest separation of aspartame, benzoic acid, and caffeine? Well, in this case, this is this distance, this is distance, and this is just a estimation, but okay. And okay, so there is a large separation from all of them. As you can see, there's a lot of separation. So, but wait. What I can see is, the separation is actually equal to this retention time thing. So as you can see, this retention time from here to here is, benzoic acid and aspartame. So benzoic acid is here and aspartame is here. And then we know that aspartame to caffeine is like this distance, which means that it's this long distance. As you can, so in other words, this here is actually giving us the distance, the separation distance. That's actually going to be helpful because we don't have to draw a lot of these diagrams for every pH. So, for example, in terms of separation, this is widely separated, as you can, from all of them. Whereas here, it gets less, as you can see. The separation gets smaller in comparison to pH of 3. What about 4? 4, there's a problem. These are very close. These are very, very close. In this case here, this is still much larger, as you can see. The separation is much larger, whereas this one is quite smaller. And this one also rubbish because these two together are on top of each other, so there's a small separation. So the biggest actually one that actually has the most separation is in pH of 3. So A. Yeah. Perfect. So when you're doing these questions, I want you guys to kind of draw, really think about it. So draw a diagram like this and see, okay, these over here, these distances, I was going to draw actually over all of the 4 for each and kind of, measure them. But you don't need to do that because this distance is the same as this distance. This distance over here is the same as this distance. And you can actually kind of measure those. So perfect. Nice question. Question 8A. Question 9. Which of the following would minimize sources of error and uncertainty in the student's experiment? Okay, let's look at that. Dilute the samples of soft drinks prior to analysis by... I think that just makes it... I think it just makes a lot of problems because... especially the pH. If you're dilating the pH, it's going to just change the pH for all. So, it's not a... And remember, if you're diluting it, for example, benzoic acid is an acid. Aspartame, I have no idea what it... we know how the structure is. Caffeine, we don't know the structure of caffeine. So, it kind of just affects too much of these values, like the pH. And so I wouldn't... That's too much problems. It wouldn't actually minimize it, but it would actually create more uncertainty in their answers. Use different mobile phases for each type of soft drink investigated. Why would you do that? Because how are we going to compare the retention times if we're using every time different mobile phases? That's not very good because, So C, analyze 3 allocates of each sample of soft drink through the HPLC instrument. Okay, that's actually quite good because you know what you're just doing? You're just repeating the experiment. If you're using 3 different using the 3 allocates of each sample of soft drink through HPLC, what you've done is you're actually increasing your accuracy and hence you're minimizing your uncertainty and error. So that's actually great. Always remember, repeating an experiment is great because it minimizes random error and So Next question, increase the pH of the samples of soft drinks by adding hydrochloric acid. Again, why would we want to increase pH? It just really makes so much uncertainty. We're gonna have problems, you know. pH with this scale will be totally different. And remember, some of them are, you know, high in acid, and whereas some are basic. It's just gonna totally mess up our HPLC. It just makes it too much confusion. So I wouldn't say yeah. The only possible answer would be probably C. A nice question. Question 10. A researcher uses a combination of spectroscopic techniques to determine the structure of molecule. Which combination of spectroscopic techniques provide the most information about the molecule's functional groups and number of carbon environments? You should straight away know. When we're talking about carbon environment, it is carbon NMR. Straight away. 13 carbon NMR. You should straight away. When you're talking about functional group, the one that gives us is the infrared. Remember, if you look at your data book, the infrared actually gives us all about information. Like, for example, here is the infrared. As you can see, these are all functional groups. So it's the one that actually gives us the functional group of the molecule. So it would be infrared and carbon NMR. So 10 would be B. Mass spectrometry, don't use that. Mass spectrometry will be useful in determining the molar mass of the molecule and the fragments. But yeah, very useless in this case. And remember, hydrogen NMR is used to find out the hydrogen environment. So only B would be the best in that one. Question 11. Ethane, 1,2, this, whatever, is commonly used in antifreeze and is a precursor for the polyester fibers. It is synthesized from the reaction of oxyran, this, with water, according to this following equation. Okay, so we've given an equation, that's nice. In an industrial process, 86 grams of this over here, oxyran, reacts to produce 86 grams of this over here. And we've given the molar masses of everything. The percentage yield for this process is what? So the way you calculate percentage yield is in your actual formula sheet. So you go to your formula sheet and you can just go on top. If you don't know, here it is. Percentage yield, so yield, right over here, is actually the actual yield divided by the theoretical yield times by 100, which is a percentage. So when your yield is in grams, by the way, it's measured in grams. So, okay, let's go here. So in this case, we can actually calculate the theoretical yield using this over here to calculate the theoretical yield that we're creating of this. So if we, we can use, like mole ratios and stuff, and we'll calculate the theoretical yield. So the theoretical yield will be here. So I'm going to write theoretical yield. The top is the actual yield. Well, in this case, it actually produced 86 grams. So we can put 86 on the top. So that's right, 86 divided by the theoretical yield, which will be at the bottom, and we times it by 100 to make it a percentage. And it's now easy to, let's calculate the theoretical yield. Well, let's find the number of moles of C2H4O, which is going to be 86.0, 86 grams, and we're going to divide it by its molar mass, which we are given is 44. So what's 86, 44? That's going to be, let's rub this all out, 1.95 mole. Because it's a 1-to-1 ratio, this is actually equal still to the number of moles of C2H6O2. So that's great. Now we just need to multiply this to get the mass of C2H6O2. It's going to, the mole of it, which in this case is still 1.95, and we're going to multiply it by the molar mass, which is 62. Times it by 62. And we are given, it's actually 121.18. So let's put that in our calculator. What's 86 divided by that? Times it by 100, and we get 70 so we get 70.96, which is around 71% actually, just 71%. Choose D. Nice and easy. Question 12. The cathode reaction for a particular alkaline fuel cell is given. Remember, alkaline. So we're going to have OHs in it. The only product of the overall fuel cell is water. Remember? Only product. The half equation that represents this anode reaction is what? Well, okay. So if I was drawing it like a fuel cell, it's easy. I can, you can easily quicker, but I want to really represent how it looks. So imagine a fuel cell, yeah? And you have, well, actually, let me draw it bigger. Just imagine a big fuel cell here, where we have substance preparation. This is where your electrolyte is, especially that it's alkaline. Let's say it's just OH minus. And okay, of course, we're gonna put our fuel. For example, our fuel's we are reacting oxygen gas, so this is oxygen gas, and the fuel in this case will be H2 gas. Remember, we're producing water, and so let's think. We know that anytime in the fuel cells that oxygen reacts, it's always going to be occurring at the cathode, where reduction occurs, and this one here at the anode. Okay, that's great. And yeah, so knowing this, and the byproduct is water, let's really look at this. The half equation that represents the anode is what? Okay, so what I'm going to do is, remember there's going to be OHs into it. There should never be H+. If there's H+, it's like thinking it's a acidic. It's an acidic environment, which is not. It's a basic environment. Be careful. When you see H+, make sure those are wrong. Absolutely wrong. Even this one has a H+. Beautiful. Can you see how these ones, this one, doesn't look all right. It doesn't looks all right because it doesn't have H+, and this one also has OHs. This looks nice. Now, let's start thinking. Now, if I just rub this whole thing in, and let's take equation B as your answer. The way you actually check is, for example, let's write this down. O2 plus 2H2O plus 4 electrons goes to OH minus. This one, if we're taking this one, remember, I'm going to multiply by 2, like all of it by 2, because I want to make sure the electrons are the same, because I'm going to try to find the overall reaction. And if I find that overall reaction, what is the product? If the product is water, it's beautiful. That's the only product that you should have. So if I multiply everything by 2, so 2H2, for example, plus 2O2 minus goes to 2H2 plus 4E minus. What do we see? Well, the electrons can cancel out nicely. The water cancels out. Wait. If the water is cancelling out, that's not good. The products are going to be like OH and stuff. That's rubbish. No. So it cannot be that one. It can only be D as your answer. And let's check. Let's redraw this. So O2 plus 2H2 plus 4 electrons go to 4OH minus. So imagine multiplying this whole by 2, so we make the electrons equal to each other. So H2 to OH minus. Sorry, 4. What am I doing? So that's a 2 here, plus 4OH minus, 4H2O, plus 4 electrons. Those electrons can cancel out nicely. The water, we get 2 waters here. Those OHs cancel out, and that's it. So we get O2 plus 2H2, and that gives us 2H2O. That's it. Look how perfect this is. We get these reacting, and it creates only water as your byproduct. That is perfect. So that's Question 13. Which of the following fatty acids would be expected to have a higher melting point? Now, you should know something about fatty acids. Fatty acids, to determine their actual melting point, we need to look at if they're saturated, means that they actually just have single bonds. It really depends on their length. For example, their carbon length, their carbon chain length. But if they have double bonds, it's a big problem. Double bonds create kinks, and kinks are a problem because what they do is they don't let the thing come together. They don't let the fatty acid actually kind of come together, and hence destroy the melting point. Actually, very gradually, it really does. Like, for example, it will destroy it so badly. For example, if it's, say, without double bonds, it's like, let's say 40 degrees Celsius. That's the melting point. With kinks, it'll be like -2. It will actually destroy that melting point. So it's very important. The more kinks it has, so the more double bonds it has, the less its melting point is. So that's important. And so let's look at this question looking at our data book. All right. So I'm going to zoom into here. Let's look at oleic acid. So I'm going to go down to my beautiful oleic acids over here. What do we see? Well, it has a carbon chain of 18. So let's write 18. Sorry, let's write 18 carbons. So it has 18 carbons. Beautiful. And does it have any double bonds? Yes, it has one double bond. That's a problem. So let's write that down at least. One. I'm going to write it as a double bond like that. What about stearic acid? Let's look at stearic acid here, which is here. It also has 18 carbons. So it's really not affected by this, but it's all about the double bonds. And it has no double bonds. Great. No double bonds. What about linoleic acid? where is that? Which is here. It also has 18 carbons, so that's good. And so what about the double bonds? It has 2 double bonds. Okay, and then lastly, linolenic acid, which is this. It has also 18 carbons, and it has 3 double bonds. Okay, so let's compare these. Go here, back here, and really have a comparison here. Like we said, the more double bonds they have, the less their melting point is. So we straight away know that they are not affected by dispersion forces. All of them have the same carbon chain. So it's not about, we're not going to deal with that. It's all about double bonds in this case. So the only thing is the ones that don't have actually the double bond, which is only stearic acid, would have the higher melting point. Whereas this one here would have the lowest in this case. And this will be your second, this will be your third. Beautiful, nice and easy. Question 13, it's B. Question 14. 2 chemists are developing a new analytical technique. They are collecting data from experiments to determine the relationship between the electrical output of an instrument and the concentration of chemical in a solution. Test solutions were all prepared by dilution of the same freshly standardized solution of the chemical. The chemists took 4 measurements, at each concentration and average those results. The same instrument was used for all the measurements. The average data is plotted on the graph below as indicated by this symbol. Okay, so that's chemist 1, chemist 2, and the average data. Okay, and this is electrical output, and that's the concentration. Okay, not too bad. Let's look down. Using the same data plots, the 2 chemists made different hypotheses. Chemist 1 hypothesized that the relationship between the electrical output and the concentration is a curved graph. So chemist 1, which is those little dots, yes, he can see it. Can you see how it's like a little bit much curved for chemist 1? So yeah, for him it looks like a curved graph, indicated by the dotted lines. Chemist 2 hypothesized that the relationship is a straight line, indicated by the dashed line. So chemist 1, which is this, yes, here's one he believes, yeah, it's a straight line, as you can see. How should the chemists do to test their hypothesis? Well, they want to check if it's like a linear relationship or a curved relationship. The way you should do it in a real thing is to actually plot more points. For example, the more higher concentrations. And what's that going to do is it's actually just going to really show you what's going to happen. It's going to go as a curve, which you can say it's a curve relationship, or it could, in the long term, like drawing, taking more points of concentration, so like longer points. So it could be like, it could be like a curve, or it could be like a straight line. It could be a straight line. And if it is a straight line, that's perfect. So it is a linear relationship. Or it could be a curve like that. So the way you actually would try to test the hypothesis is by plotting more points, plotting more concentration points. What should the chemists do to test the hypothesis? Measure new test solutions. What is that going to do, really? It's not going to really help. Look, measuring test solution is just going to make, it's going to accurately determine of these points still the same. It's not like it's not really going to help just measuring a new test solution. It would probably be the same point, and the relationship will look the same, but we really can determine, but the main thing is we're trying to determine if it's a curve or a line graph. So determining a new test solution will only wouldn't actually, it would just make them more accurate. These points will be more accurate if you're using, so it's not, and in other words, we're increasing accuracy. We're actually not are we solving the solution, the hypothesis? Standardize the chemical solution again, that's also, just trying to make sure it be more accurate, which is not very helpful in this case. Being more accurate makes the standardized data more accurate, which it's not going to really help us see the relationship. So what about take 6 measurements at each concentration? No. If we've taken 4 and we're taking 6 measurements and we're averaging them, it will still be approximately still the same points. And if we're taking this, really, it's not really going to be that helpful. But it could, but not that helpful. What about the next one? Take measurements at a higher concentration of... This is that it. If you're taking taking measurements of high concentration of the chemical, as we're saying here, if you take, the high concentration and, you plot those points, you will actually see what the curve looks like. Does it look like a curve, or does it look like a linear proportionality? So D would be the best here, I would say. C can also be true. I'm not going to lie, take 6 measurements of it. But I think it's just going to make them more accurate, those points. He's not really... Yeah, in terms of seeing, yeah, so I would say D would be the best. I need to check the answer actually for that one. 14D. 15. How many structural isomers can be drawn for this? Beautiful question, commonly in exams. So the way I would always do it is, okay, so I'm going to draw these 3 carbons, and so I'm going to say bromine here, and let's say Cl here, and yeah, that's 1 right here. Okay, that's 1. And if I take this bromine and put it here, let's see, that could be Cl here. That's 2. And if I take this chlorine and put it over here, so Cl here, that's 3. And what about if I take this bromine and put it here? That's 4. What else can we do without repeating each other? Because if I put this here, it's going to be the same molecule as this, so we need to be careful. The chlorine. What about if we put the chlorine here? So C, chlorine, bromine, C this, C that. And that's a totally different molecule. Is that it? I want to double check. So we have chlorine there, we put it there, also done that. Okay, we've also done that. Yeah, those are the only, and if you just move them more, they'll just be the same molecule. And that's how many? That's 1, 2, 3, 4, 5. We have 5 structural isomers. Nice. Next question, the 16. The only gaseous product in a reaction is carbon dioxide. This gas is collected in a sealed and previously evacuated 700 milliliter container at a temperature of 28 degrees Celsius. The pressure in the container is 200 kilopascals. The mass of CO2 is produced is closest to what? Oh, beautiful, nice question. You should straight away know which formula to use here. PV and RT, the gas formula. Well, in this case, we want to calculate N, the mole, so PV. RT equals N. And so N, what's P? The pressure has to be in kilopascal, which it is, so 200. Volume has to be in liters, so it'd be 750 times 10 to the negative 3 to make it into liters. Divided by, what else? R, which is 8.31. It's a constant which you can find in your data booklet. T is the temperature in Kelvin, so it'll be 28 degrees plus 273 to make it into Kelvin. And that's it. Let's do that. 200, 750, negative 3, 8.31, 28 plus 273. Okay, so we got N is equal to 0.0599 mole. Now we need to convert it to mass. So remember, mass of CO2 is going to be this mole multiplied by, let me actually move this, multiplied by its molar mass, which is, molar mass is this, or is what? So carbon is just 12, and 16 times 2, because there's 2 hydrogens, so that's 32. So it'll be 12 plus 32. So let's do that. 12 plus 32. That'll give me 2.63. So B is the answer for that one. 16B. Nice. 17. Which of the following statements regarding titrations is correct? Okay. Let's look at this. Let's use a different color. Let's use this color. I can't even say this. Phenolphthalein is an appropriate indicator to use for a titration of ethanol against acidified potassium permanganate. Okay, let's have a look at this. Phenolphthalein, we need to double check if it's, if the pH range is perfect. So for example, if you just go into your, okay, here's your acid-base titrant. That's phenolphthalein, this one over here. The pH range is high, meaning it's used for basic if the pH is large. If we're using ethanol, which is, if you don't know, it's a weak, sorry, my apologies. It's a weak acid. And acidified acidified, it's probably acidified. So if you're putting an acid and an acid, it's very low in pH. So, and remember, using phenolphthalein is normally for high pHs, so it wouldn't be the best in this case. The most appropriate indicator for the titration of a weak acid with a strong base is methyl red. Okay, so imagine weak acid. So what? So 7, the pH of 7 is water. Like, that's the neutral. And if you go below that, that's like around 6 to 5. That's actually a weak acid. So let's say we approximately pH of 6. That's the weak acid here in this case. So pH of, let's say, 6. That is for a weak acid. If you're reacting with a strong base, well, the strong base is going to overpower it. It's going to be like 8, 9 at that point. We're going to mix it. So the pH will increase. Let's say 8, 9. So methyl red, let's look at methyl red. Is it going to be in that range, like 8, 9 or 8, 10, around those? So we're using methyl red. Where is methyl red? Methyl red's over here. And it's 4.4 to 6.8. That's rubbish. We want like a very high pH. So that's not the correct answer for that one. So that's rubbish. C. Dilute solutions of strong bases can be titrated more accurately than concentrated solution. I have no idea. I'm just going to put a question mark on there. Next, what about D? Distilled water should be used for the final rinse of all glassware that will be used in the rubbish. You never ever used water to clean all the glassware. Remember, the burette has to be rinsed with the standardized solution. Why would you not? Why we don't actually, mix, rinse the glassware with distilled? That's going to decrease, and it's going to really affect our concentration. Like, for example, if you're going to distill water, our burette, which is supposed to contain our standardized solution, it will decrease the concentration of it. So it's not even standardized at that point. So rubbish. Then hence C should be the only answer. So dilute solutions of strong bases can be titrated more accurately than concentrated solutions. Yeah, that is probably the most best answer there. Question 18. A compound with a formula this has the following features. So it has 2 oxygens, 6 carbons and 12 hydrogens. It is unbranched, so that's good. It only has 1 type of functional group. All carbon-to-carbon bonds are single bonds. Great. The compound could be classified as what? An ester group? Well, an ester group looks like it has this, so it does luckily have 2 oxygens, which also an ester group has 2 oxygens. We can put a tick there. Is it an amide? So remember, an amide group looks like, let me do that, like this. It has to have a nitrogen. In this case, we don't even have nitrogen. That's rubbish. Alcohol has an OH. Remember, it only has 1 O. It doesn't have actually 2, so that's wrong. Aldehyde. An aldehyde has, for example, it looks like this, where it has only 1 oxygen. So it cannot be an aldehyde. So, because we have 2 oxygen, so it can only be an ester group. Nice and easy. Wow. What about question 19? The diagram below shows concentration versus time graphs for 2 different reactions under identical conditions. The graphs can be used to determine whether each reaction is reversible or irreversible and which reactions has a faster reaction rate. Remember, when you're looking at a concentration time graph, if the reaction is in equilibrium, it is reversible. That's what we know. We know because if you don't know, that's most of the... for example, if you, so in equilibrium, what do we mean by equilibrium? So if we increase like the rate of if we increase like the concentration of the product, they will come back and to a constant concentration, as you can see. Like here, let's look at reaction 1 in this case. We can see that we started over here. This is G. There was, of course, concentration 0, that it was initially nothing in there. But as time progresses, as we can see, it becomes a constant value because it's reaching equilibrium. And so what do we know? We know that equilibrium reactions are a type of reversible reactions. Remember. So, and when a system's in equilibrium, which we can easily plot here, when they actually reach equilibrium, they become like a straight line. As you can see, they're reaching equilibrium where we're reaching a constant concentration for both product and reactants. So we know that it has to be a reversible reaction. So absolutely be careful. It's not a reversible. It has to be a reversible reaction when we're dealing with equilibrium. So let's look at this. Which of the following conclusion matches the data present in the graph? Reaction 1. Well, both reactions are reversible, by the way. As you can see, they reach equilibrium. So B and C are wrong. Rate of reaction. Reaction 1 is slower than reaction 2. The way you actually determine which reaction is faster is, okay, well, when do they reach equilibrium? How fast do they reach equilibrium? For example, let's look at reaction 1. Well, we can see that it's reaching equilibrium approximately at 120 seconds, whereas this one over here reaches equilibrium at 90 seconds. So which one's quicker? Absolutely reaction 2, because it takes 90 seconds to reach equilibrium, whereas this is 120. So we know that reaction 2 is faster than reaction 1. So reaction 1 is slower than reaction. That's true. Yep. And then, yeah, that's pretty much your answer. Is that one? Yeah, 19A would be the best one, where we know that reaction 1 is slow. Done. Question 20. In Year 12 chemistry, so a Year 12 chemistry student is revising enzymes and coenzymes and producing the diagram below to summarize what occurs during a reaction. Unfortunately, the student has made a significant mistake. Let's see what he's made. So we can see that this is your enzyme. We have a coenzyme. Beautiful. And of course, the coenzyme just binds to the active site, and it kind of makes a space for the substrate to fit in nicely. And perfect. The substrate is in. We can see that after the enzyme, it's not affected. Beautiful. That's true. The product is affected, of course, because like if it's a breakdown, product's going to get broken down. That's great. Aha. Coenzyme. Why is the coenzyme broken down too? A coenzyme is not affected in a reaction. It comes out unaffected. So, for example, you know this enzyme here, it comes unaffected. A coenzyme has the same thing. It should be not affected. Why is it broken down? Initially, it starts here and it's broken down. So, that's pretty much the mistake. That's the mistake. Which of the following statement best describes the significant mistake represented in the student's diagrams? An enzyme's active site is specific. That's true. And will fit only one substrate. Yeah, like what? That's not going to explain why he's made that mistake, so I don't know what that is. A coenzyme binds with the enzyme, okay, to change the shape of the active site. That's true, but it's not. That's not the mistake. The mistake is like after the. Why is the coenzyme broken? An enzyme structure is irreversibly changed. That has nothing to do with it. What about D? And a coenzyme breaks apart during... This is the problem. Yes, a coenzyme breaks apart during a reaction. Why is it broken down? It's not supposed to be broken down, a coenzyme. So, easy. 21. Chromate this and dichromate, which is this, ions in solutions reach equilibrium as shown in the following equation. To increase the concentration of CrO4, so we want to increase this concentration of this. Yeah, that's the one. Yeah. In a solution at equilibrium, a student could add a few drops of what? H2O. So imagine, okay, let's say he does add up H2O. Now, a lot of students, be careful. Students will be like, oh, you're adding H2O, so you're increasing the concentration of H2O, so the reaction should go to the left, and it's increasing the rubbish. Be careful, don't do that. So, when we're adding H2O, we're pretty much, this is the thing that's going to affect. So, imagine we're adding H2O, we're going to be diluting this. Imagine the more H2O we add, the more the concentration of this here dilutes. It becomes less. So imagine, okay, we lessen this here. And what's going to happen? The system's going to be like, wait. I need to compensate for that. So I'm going to move to the right to compensate. So it can actually compensate for that. If it moves to the right, that's a problem. We want it to move to the left so we can actually produce more to increase that concentration. So if it moves to the right, it's not increasing, it's actually decreasing. So A is wrong. Nice. Let's look at the next part. HCl, so if we add hydrochloric acid, which is a very acid, what's it going to do? It's actually going to increase our H plus ions. Remember, hydronium ions are pretty much all related to, think of an acid, like it's acid, H plus ions. So if you're adding HCl, which is hydrochloric acid, and you're adding more, you're increasing these H plus ions. And if we increase it, the system's like, wait, that's too much. I need to get rid of that. So it's going to turn to the right to get rid of it. Again, it's not turning to the left, so that's rubbish. It's not going to actually increase the ions. NaCl, I have no idea what NaCl is going to do in this reaction because, I don't know, like NaCl. In this case, it's not very helpful because we have, like, water, H plus is used for, like, you know, acid and stuff. But NaCl, I don't know. I want to put a question mark on that. I have no idea what NaCl will do. Like, because I don't know if it's acid or like this. It's like, yeah. We'll put a question mark. What about the next one? NaOH. Now, you know sodium hydroxide is what? It is a strong base. So what does that do? If you mix a strong base, and remember, this is acidified, as you can, that 2H plus, that's like acid. So if you're putting a strong base, what's going to happen? It's actually going to decrease those H plus ions. So if it decreases, the system is going to be like, wait, I need to increase that. So it's going to go to the left. Yes, if it goes to the left, it actually increases the concentration of CrO4 2 minus. So beautiful. 21 is D. Question 22, which based on the pathway shown above, which of the following correctly identify compound K and reagent L when this is produced? So okay, let's look at this. We have this, so let's draw that. That's a C, double C here, and H here. Okay, and so when it's reacted with water, when that actually happens, when you react with water, what's going to happen? Well, we're going to have that double bond breaks, of course. So, and we're going to have a OH then. We're going to have an OH, which is what happened here. Okay. By the way, that OH can be actually put, remember, because it was a double bond, we need to be careful. That OH could be also put, it could be put over here. So it could be both put in the, yeah. Because you remember the carbon double bond? The carbon double bond tells us where it would be put. So, for example, it could be in this carbon or this carbon. So, okay. But it's put in the last one. So that's important. Let's have a look at this. So if we have this and we're adding hydrochloric acid, what's going to happen? Well, that H of hydrochloric acid will be here and it will break down that double bond. So it'll be C and it'll be just a Cl. Nice. It would just be this. Now, this chlorine can actually be on top. Remember? It's same as the OH, or yeah. But we're putting it over here. Oh, yeah. We have to put it over here. Be careful. We actually have to put it over here. Why? If we put the chlorine on, let's say, this over here. For example, if you put it over this one. Am I doing the right one? Two. Need to be careful, so not that. If I put the chlorine over here, what's going to happen? When we actually react it, let's say, it's going to be compound K, of course, and then we react with a reagent, the OH, that will create, of course, alcohol. The alcohol will actually just substitute with the Cl, and the OH would be over here, which in this case is not true because the OH is on the right side, on the end. So it has to be a Cl on the end of it. So nice and easy. So we're going to put a Cl at the end of it. So compound K is going to be 1, 2, 3, 4. So it's going to be, it's a butane, and it's going to be at the first carbon. So 1 chlorobutane. So B and C are wrong. Now what's reagent L? Of course, it's going to be water. Remember when you mix water, for example, it's going to be, it's going to substitute with the Cl. It's going to have an OH here, which is what this is. So yeah, C is your answer. Remember, you have to look at your reaction pathways, so make sure you memorize those. It's also in my thing here. If you guys don't have it, I also have it in my data book right over here, so I can memorize it. Here it is. So for example, here we went from an alkene, so in this case alkene, and we reacted it with HCl, hydrochloric acid, which we can also say HBr, same thing. And it's going to give us what? Can you see how it could give us this part over here, which in this case is, 1 chlorobutane. And if we react it with a reagent, which in this case is H2O, as you can see here, what it becomes an alcohol. Beautiful, that's why. So, nice and easy question. That's 22. So the next question. All right. 23. Says 0.5 grams of ethane. This undergoes complete combustion in a bomb calorimeter containing 200 milliliters of water. The water temperature rises from 22 to 48.5. The thermochemical equation for this combustion is this. Using this information is what? Okay. Well, first, we've given a lot of equations. First, we have to check if they are balanced first. Let's check if they are balanced. So we have 2 carbons here. 2 carbons, great. 6 hydrogens. 6 hydrogens, great. Oxygen, we have 10 here. And we have 4 plus 3. That's 7. No, that's wrong. What about the next one? 4 carbons, great, as you can see. 600, wait, we have, yeah, so 12 hydrogens and 12 hydrogens. 14 oxygens. That's 8 plus 6. Yes, 14. Great. B looks like a great equation. This is the same as this equation, so C is wrong. And also, yeah, B and D look good, the equations. Now, the difference between them is the enthalpy change. Well, it's easy to actually calculate enthalpy change. Remember, be careful. You might just go to ethane and go to your data book and just start to look at ethane. What is the, like, go down here and look at the SLC heat combustion. For example, ethane. Is this methane? Yeah. Ethane, yeah. Ethane, which is over here, it's 1560. And because there's 2 moles of it, you're going to multiply by 2 and be like, oh, it's this one over here, isn't it? Be careful, that's wrong. We're using calorimetry, which it's not going to have that exact value of CLC. It's actually going to be totally different. So make sure to use the calculations that you're supposed to use. For example, if we have 200 milliliters of water, which we need to convert it to grams, the way to do that is this 200 milliliters, we're going to multiply it by this constant. It's in your formula sheet to get it into grams. That's only for water. Where is it? Over here. Right over here. This part here. So it's going to be 0.997. Great. So what's 200 times, 0.997. That's going to give me 199.4 grams. So we have the, so energy is equal to MC delta T. So that times that 4.18, which is the specific heat capacity of water, times your change in temperature, which is what's 48.5 minus 22. That's, sorry, what's 48.5 minus 22? That's 26.5. So here, doing all this should give me 19.4. This actually gives me the energy. So that's done. That gives me 22087.5. That's in joules. So we want to make sure it's in kilojoules because these are the units that we're going to be using. So divided by 1,000. And that's going to give us 22.0875 kilojoules. Now, the final thing is we need to get the mole. Remember, it's kilojoules per mole. So to get the mole, if we have 0.5 grams of ethane, it's easy to get the moles. The number of moles of, for example, ethane is going to be the mass divided by like the molar mass, which is 2 times 12, because we have 2 carbons and plus 6 hydrogens. So it's going to be 0.5, 2 times 12 plus 6, and that's going to give me 0.01666, all this big number. And yeah, we're just going to divide that to get the change in H. Take this over here, divided by this over here, the mole. And that here should give us, so what's 22.0875 divided by that. And we get 1325.25. Be careful. That is not your full answer. I'm actually, it's negative because it's a combustion reaction. Be careful, that's not full answer. Because we have 2 moles of it, we have to multiply by 2. So imagine multiplying by 2. That gives me my final answer. So I'm just going to rub this whole thing off. And that gives me, as a final answer, 2650.5 kilojoules. Which is approximately this one over here. So choose D. Done. Easy. Question 24. Okay. So it says, a particular HPLC instrument was used to separate mixtures of 2 chemicals. Each separation was done under similar conditions. The mobile phase was used either was water or hexane, and the same stationary phase was used for each separation. For the mobile phase given in the first column, which of the following option gives the 2 chemicals expected to have the largest difference in the retention time? Wait, so it's the chemicals is like, okay, maybe if that makes sense. Are these chemicals mixed in like with the stationary phase, and they are the stationary phase? Is that what the question's telling us? I'm very confused. Okay, I think, yeah, it's like they're mixed with the stationary phase. For example, let's look at A. For example, let's say the stationary phase was butanoic acid as the first one. And the hexane is the mobile phase. Well, butanoic acid is a polar, thing. It's very polar. And if you're putting hexane is non-polar, so it's going to go quickly down. It's actually not going to mix up. It's just going to. So what do we know? Imagine like in, let's say, like 3 seconds, it'll straight away go down here. That's what's going to happen with hexane. It's just going to go quickly down. Whereas butane's actually non-polar, so it's actually going to be sticking to us. So let's say in 3 seconds, it will actually be over here. So the difference is what? It's actually quite large. So that's good. So we can say that's great. That gives us some large retention time. Let's look at the next case. So same thing. So let's just draw a nice. So water and acetic acid. So let's say acetic acid was used. So the problem with acetic acid, it's a polar, and water is also polar, so they're going to be sticking together. So they say in 3 seconds, they haven't moved a lot. Whereas if you're using ethanol, also ethanol is polar. So, but I think ethanol is much like a little bit much non-polar. Like it has polar, so it would be like in the middle. So, but the difference, A has a bigger difference. I wouldn't say it's much bigger, so I'd say B is wrong. Look, A looks very. Oh, why am I rubbing this out? Let's try the next one. Hexane, ethanol. So we know if hexane is going to go straight away down because it's non-polar, whereas ethanol is polar, so it'll go down here. We're done. Whereas methanol will also go like, because methanol is polar, whereas hexane is non-polar, so it will be going like less down because it's methanol. Like, whereas wait, what am I doing? No. So my apologies. Ethanol will be much attracted because it has a longer polar, non-polar group. So it'll be like on here, whereas methanol, which is much stronger polar because it has a meth group, so hexane will be much more it will go more down than ethanol. So, but still the difference is very small, so there isn't, still wrong. Next one, water. So butane and octane. So imagine butane was used in this case. Water would straight away, it's non-polar, so straight away it'll go down quick. It wouldn't want to be like mixing around with it. And octane, even worse. Octane's like much down. So still the difference is very, very small. So only A would have the largest distance in the retention time in this case. Yeah, I hope that's an easy explanation to do. 25. Let's look at 25. A student aims to calculate the theoretical amount of energy available to the body from cellular respiration using the oxygen gas O2 retained by the body in a normal breath. In this calculation, the student assumes that the energy released at normal body temperature is the same as that released at standard laboratory conditions. Okay, so as SLC. So we're probably going to use N equals V over Vm. 19.6 milliliters of O2 is retained by the body in a normal breath, okay? A balanced thermochemical equation for the cellular respiration with glucose as the primary reactant is shown. Okay, that's good. The theoretical amount of energy produced from cellular respiration from O2 retained by the body in the normal breath would be what? Nice and easy, actually. So, well, let's find the mole. Like, we need to first find the mole of oxygen gas, which is easy. It's just going to be the volume of it, which in this case is 19.6 times 10 to the negative 3 divided by the Vm, which in this case would have been 24.8 in your formula sheet. So what's 19.6 times to the negative 3 divided by 24.8? That's going to be 0.00079 mole. So we have the number of moles of oxygen, but be careful. We're going to divide. We want like 1 mole of oxygen. Here we have 6 moles, so we need to divide it by 6. So a lot of students might forget about that, yeah. So make sure you divide it by 6, which is going to be 0.000131 mole. Then lastly, guess what? We just have to multiply it by this here. So, because that's going to give us, yeah, that's kilojoules per mole. So, times that by 2816. And that gives me 0.3709247 kilojoules. Remember, it's in kilojoules. So, which looks like B is your answer for that one in scientific notation. Easy. 26. An electrolysis cell is made up of a 500 milliliters solution of metal salt with two inert electrodes. A current of 3 amps is applied for 1 hour, and 1.9 grams of metal is deposited on the cathode. The 500 milliliter solution was used in this electrolysis cell is used what? It's such a beautiful question because it's always repeated in exams most of the time. I've done this question so many times in exams, past exams. First, what I'm going to do is, okay, first I'm going to find the charge. No charge is current times time. Well, in this case, current 3, and the time is, we need it in seconds, so it'll be, because it's 1 hour, it's like 1 times 60, and that's in minutes, times 60 again to get it in seconds. So that's going to be, what's the charge of that? It's 3 times 60 times 60. That's 10800 coulombs. And then we want to get the number of electrons, the mole of electrons, which is 10800 divided by the Faraday's law, a constant which is in your data book, I think, yeah. So 96500, and that gives me the number of moles of electrons. Beautiful. So let's write that down. So it's 0.1119 moles. So we don't need nothing now. We just need that. And what we're going to do is, okay, if I know how much metal is deposited, for example, let's take this one, the first case, copper. Now this is, copper 2 plus 2 electrons goes to copper solid. So if we have 1.9 metal, so it means we can find the, copper metal, the mole of that, which is, 1.9 divided by, what is copper? What it's molar mass. Copper is 63.5. Okay, so we have copper. That's good. I'm actually just gonna write all of the molar masses of the other one. So like copper is that. Ag. What's Ag? What's that? Ag is 107.9. And chromium, which is the next one, 52. That's it. So I don't want to look at my periodic table anymore. I just want to do the question. So that's going to give me what? So what's 1.9 divided by 63.5. Sorry, 1.9 divided by 63.5. And that's going to give me the number of moles, which is 0.0299. Great, that's the number of moles. So if I want to calculate the number of moles of electrons, if I calculate the number of moles of electrons, it should be equal to this, shouldn't it? So number of moles of electrons is what? It's going to be the number of moles of copper times the ratio, which is 2 to 1. This is 2 to 1, which is 2 to 1, which is that times 2. And that is going to give me 0.0598, which is not the same as this. So it cannot be copper. It cannot be that one. Let's look at the different case now. That's wrong. Also, B is wrong, by the way. It's just the concentration is different, but it's still copper. It's still the same thing. It really doesn't, nothing, concentration doesn't do anything. It's all about the, copper. Okay. Next one is Ag, which is silver. So Ag is Ag plus E goes to Ag solid. So save here Ag, number of moles of Ag, which is going to be 1.9. So we have mass. What's the Ag? It's 107.9. 1.9 divided by 107.9. And that's going to give me 0.0176 moles. And now I have that, and because it's a 1-to-1 ratio, that's equal to the number of electrons, which is not the same as that. So C is wrong. So chromium looks like the only answer left, so let's try chromium lastly. So chromium will be chromium 3 plus 3e goes to Cr solid. So number of moles of chromium is going to be 1.9 divided by 52. And so we get 0.0365 moles. And remember, it's a 3-to-1 ratio, so imagine to get the number of electrons, it's going to be 3 times this here. Which is beautiful. It's 0.1096, which it can be so similar, as you can see. If this is so similar, so it can be D as your answer. 0.1, this is just, if you're putting that may pretty much like oversimplifying, it's just 1. Yeah, it's still closest one, so D is your answer for that one. Nice, that was not bad as I thought. Very common question, so make sure you know how to do that. Question 27. Let's look at this. The Max-Boltzmann distribution curve below represents the kinetic energies of molecules in a reaction with an activation energy of 7 arbitrary units. Okay. So, okay. Which of the following shows the distribution curve with the highest proportion of successful collision? Now, what do we know? For the highest proportion of successful collision, what is it? It's the... we'll actually do the question. So, if I know that activation energy is 7, which is around here, what do we know? The ones that have the highest proportion of successful collision are ones on the right. The ones that actually... So, this is the activation energy. It's the ones that go above and beyond this activation energy. And those are the ones that have the highest proportion of successful collision. In this case, well, the area here is good. Like, it's enough. Like, that's good. Well, but let's try the next one. Well, if this is the activation energy here, really doesn't have anything to the right. Like, nothing's going above that. So, that's a problem. Doesn't look like that. See? So, 7's here. Look at this one. Oosh. The area here is much larger than this one. So, this one has a higher proportion of successful collisions. And then this one here, only this little bit. So, C looks like the best one. Nice and easy. Yep. So, 28. A student's breakfast consists of mashed avocados, feta cheese, and poached eggs on a slice of rye bread. The nutritional information for each component of the breakfast is shown in the table below. So we have the servings of avocado. Okay, nice and easy. The component of this breakfast that provides the large amount of energy per serve is what? Okay, that's not too bad. So let's look at first avocado. So for per serve, let's look at the per serve of avocado. Avo, let's write A. Well, we have, remember, so let's write the energy contents for proteins and stuff. So let's go down here. Going down to energy. Here we go. So for, let's write it here. Carbs, it's 16. Protein, it's 17. And fats, it's 37. That's all I'm going to need to do this question. They are so common in exams. So very important to know how to do those. All right. So let's try this. So for avocados, we know that there is a 1.34 protein. So 1.34 times protein, which is 17, plus 10.5 times the fat, which is 37, plus 5.9 times 16, which is the carbs. So, and that's going to give me, what is that? Let's see, in kilojoules. How much energy would that give me? And we want to check which one's the highest. So 1.34 times 17 plus 10.5 times 37 plus 5.9 times 16. And that gives me 5.68 kilojoules. Okay. That's for avocados, and let's try to check for eggs. I'm just gonna, because it's too confusing, I'm just gonna take this out here now. That's all I'm gonna write. That's for avocados. Put that there. Done. Next one is eggs. For eggs, E, let's call it, actually put it here. Eggs is what? Well, okay, same thing. So how much, so we have 12.7 times for protein, which is 17, plus 10.3 times 37, plus 1.4 times the carbs, which is 16. So that's going to give us 12.7 times 17 plus 10.3 times 37 plus 1.4 times 16, and that gives me 619 kilojoules. All right, so it's much higher than avocado, the serving size of avocados. Let's put that over here. Nice. Next one is feta cheese. So let me bring this up here. There we go. So for feta cheese, we have 3 grams of protein, so 16 times 7 plus 3.6 times 37 for fats, plus, well, less than 1 point, let's say 0.9. Let's less than 1 gram. 0.9 times carbs, which is 16. How much is that going to give me? That's going to give me 198. 198, so 198. Let's write that down. Here, oops, 198 kilojoules. Then the last one is rye bread, which is going to be 2.7 times protein, which is 17, plus 1.1 times, for fats it's 37, plus 13.116. Let's see what that is. Times 16. And that's going to give me 296. All right. 296 kilojoules. So the one that has the highest energy per serve is eggs. That's pretty much it. Wow, that took very long. That's it. 28. 29. Let's look at 29. Okay. Some scientists are exploring batteries that utilize the metals, potassium or calcium, as anode components. If all other aspects of the cell are the same, a cell using calcium would produce more current because what? Okay, so we want to produce more current. And what is current related to? Current is related to charge. As we can say, current is proportional to charge. So the higher the charge is, the higher the current. And we know that the number of electron is equal to charge over F. And so what does that mean? The number of electrons is proportional to the charge. So the higher the number of electrons, the higher the number of charges, which means the number of higher the charges, the number of current is higher. So because we know calcium produces more current, because calcium, Ca2 plus 2E minus goes to calcium, whereas K plus is just plus E minus goes to K. As we can see, we know that calcium produces, for every mole, it actually produces 2 moles of electrons, which is great. The more electrons we have, the more charge we have. Hence, the more current we have. Whereas potassium actually just produces 1 mole for every mole of potassium. So that's probably why. Let's look at A. Calcium produces more electrons, yes, per mole than calcium, correct. K produces more electrons per mole than calcium, rubbish. We know that calcium produces more mole. K produces a higher voltage than calcium. Let's check that out. So if I go to my electrochemical series, we can actually determine that. Which one has the highest voltage? In any case, the voltage doesn't really matter in this case because that's not what... So calcium is there and potassium. So the one that has a higher is calcium. But here, yeah, so that's wrong. Calcium has a higher voltage than potassium, so that's wrong. Calcium has a higher molar mass than potassium. That is true, but that doesn't really affect the current. What does that have to do with current? So the only possible answer that actually explains why we have more current is A, 29A. And the last and final question, 30. A reversible reaction has an enthalpy change of -50, so it is an exothermic reaction. For the forward reaction, which of the following sets of pairs of profile diagrams, one for the forward reaction and one for the reverse reaction? Okay, so if the forward reaction is negative, it has a negative enthalpy change, what do we know? It is going to have the shape of this, where this is -50. Well, then that's for the forward. But what about for the reverse? It's just going to be the opposite. So it's going to be endothermic, and it's going to have a positive enthalpy change. So it will look like this. So in terms of forward reaction, this one here is great. as you can see, it has this shape. But also this one has the shape of an exothermic. It doesn't have this shape. That's wrong. B. Okay, this shape looks nice. And also this shape looks great. Looks like the same as that. So likely to be B as your answer. We want to double check. So it's the N flip B. Yep, that's negative 50. That's positive 50. That's good. Let's check the other ones also. This one is wrong because remember we have to have an exothermic. This is endothermic for the forward reaction. D. Also, this is endothermic. It's supposed to be exothermic. So D is wrong. For the forward reaction, it's supposed to be exothermic. So the only possible answer is B. What a nice, beautiful question to end the exam. Yeah, it wasn't too bad, I would say. I've seen better exams, to be honest. But yeah, I hope, this exam helps you to understand how to answer questions. And good luck to you guys. Please make sure to like and subscribe for more future videos. It's a privilege making these videos for you guys. And take care of yourselves.